Well, greetings everyone. We're going to go ahead and start our webinar here today. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. If you need to get in touch with me, my contact information, my email address is here on screen. And I'd also encourage you to follow me and the American Segmental Bridge Institute on LinkedIn if you're not already. It's a good avenue to get announcements about upcoming events and as well as our website, but LinkedIn also tends to be another great resource for information. And also we have weekly posts about things going on in the segmental industry, look back on projects and various things. So great resource, I think. So hopefully you all are here today to hear Matt Carr talk about some of the work he has done on vessel collision studies, specifically on the Queensferry Crossing, and I'll be introducing Matt here in just a minute. Some quick announcements before we get started. Our July webinar is a little bit unique in that we will be partnering with the National Concrete Bridge Council on the webinar that they are hosting, which is a review of precast segmental bridge design resources. This is going to be presented by John Corvin with Hardesty in Hanover, and John happens to be the current president of the American Segmental Bridge Institute. What makes this webinar unique is not only are we partnering with the National Concrete Bridge Council, it's on a different day than we normally do. We usually do the last Wednesday of the month, but this month it'll be a couple weeks earlier. In July, it's a couple weeks earlier. It's on July 17th. You can register either from the ASBI website, which will redirect you then to the National Concrete Bridge Council website, or you can go to the National Concrete Bridge Council. Either way, the registration will be the same. So I'd encourage you to attend that webinar next month. Another announcement just to get on your radar and hopefully on your calendar is the 2024 convention and committee meetings that ASBI is hosting in Atlanta, Georgia at the Lowe's Atlanta Hotel in downtown Atlanta. Great part of town, lots of really great restaurants and things nearby for you outside the hours of the convention. It's October 20th through 23rd. I'd encourage you to not only get that on your calendar, but you can also begin registering. The registration is up on the ASBI website. The technical program committee is meeting next week to work out the technical program, and then we'll have that agenda posted up shortly after. We'll have over 20 technical presentations as part of the program. So again, I'd encourage you to attend. There'll be a really great wide range of topics at the convention. Another little, I will say, shameless plug for the National Concrete Bridge Council. Just 2 weeks ago, the first collaborative document that the National Concrete Bridge Council did with AASHTO was published. There's a QR code here on screen that'll take you to that document. It's a little bit hard to find right now on the AASHTO bookstore because it's a brand new publication. Also makes it a little bit of a challenge to find using a Google search. But that document was just published, and what it is, it's a catalog of all of the concrete bridge design and construction resources that we were able to identify that are held either by one of the 10 members of the National Concrete Bridge Council or AASHTO, Federal Highway, Portland Cement Association, and some other non-members of the National Concrete Bridge Council. And the idea is it gives you a single resource to find those resources that you would use in design and construction, and not just documents, but also training and certifications. Everything held by the various institutes is accessible there. We expect a lot of you all will be able to use it not only for onboarding new folks, but also experienced practitioners when you start diving into something maybe that's a little bit different. That'll be a good resource then for help you navigate and find the things you're looking for. Also, every month I reinforce that the Construction Practices Handbook from ASBI is available as a free download, and here's a QR code to it as well. It's also pretty easy to find on our website under the Learn tab, and then click Resources, and you'll scroll down and you'll find a link to the Construction Practices Handbook. We are working on an update to this. We hope to have published later this year. As a person who signs up for or checks out, if you will, the Construction Practices Handbook, will also be notifying people when the new edition comes out. So with regard to today's webinar, I think most everyone knows how to use the questions pane to type in their questions, so I won't belabor that point. Just know that you are welcome to type in any questions you have as the presentation goes, and then we'll have a moderated Q&A at the end. If you lose your connection during today's webinar, you can just rejoin by using the link you had when you logged in. You will miss content while you are away, and so bear that in mind. We are only able to issue certificates to people who attend the minimum amount of time in the webinar, and that is we're trying to be as close to an hour as possible. With regard to the certificates, I'd ask you to wait at least a week to receive an email with a link to your certificate. If it's past a week, then certainly reach out to us and we'll see what happened to your attendance certificate. Our Q&A moderator today is Wade Bonson, who's the chair of the Construction Practices Work Group for the American Segmental Bridge Institute. He's the project development manager for complex bridges for GM2 Associates. Wade's going to be watching the questions as they get put in today, and then moderating our Q&A at the end. So you look forward to Wade leading us through that part of the discussion. Our speaker today is Matt Carter. He's a principal with Arup based in New York. He has over 27 years of experience in specializing in the design and analysis of complex bridges, including cable-supported bridges and marine viaducts spanning busy navigational channels. He's led vessel collision analyses in both the Eurocode and AASHTO, coordinating inputs from maritime, geotechnical, and structural engineers, risk specialists, and advanced large displacement finite element analyses. For the Queensferry Crossing, he led a multi-phase marine risk assessment of a $1.9 billion bridge with back-to-back cable-stayed main spans of over 2,100 feet, which crosses the entrance channels to Scotland's busiest ports. And so with that, I'm going to flip over here and make Matt the presenter and give you the opportunity to share your screen.
Thanks, Greg. Let me just make sure I get it.
Yeah, you just need to start the presentation.
Great.
There it is. All right, we
me?
can hear. Yep, we can hear you just fine. So I will go on mute and turn over to you.
All right. Well, look, thank you for that introduction, and thanks everyone for coming today. And many segmental bridges cross navigable waterways, so vessel collision risk, I think, is of interest to designers of segmental bridges, and especially at the moment where this risk is in the spotlight. And if you're designing a bridge like this, there are some questions that you might reasonably ask yourself, like what would be the loss of life if this bridge collapsed? What would be the economic consequences? And what does that tell us about how strong we should make this bridge? And these are all questions that we had to address in the design of the Queensferry Crossing. It is an international case study, but it shares a lot in common with many major bridge projects in the United States. And it's an incredible value story as well. It's an award-winning structure which was delivered for about a third of the originally estimated cost, still achieving all of the client's strategic goals. A lot of the cost savings came from engineering during the preliminary engineering phase, good decisions that were made, and the client invested in giving the time and budget to allow these decisions to be investigated and made. And there's four that I often think about. There's the unique crossing cables structural system. There was a managed crossing strategy that found a sustainable use of the existing road bridge. There was the use of intelligent mobility to make the roads work smarter and have less physical infrastructure. And then the topic of today, the marine risk assessment. Just a bit of background on the project. The Queensferry Crossing is in Scotland. It connects the capital of Scotland, Edinburgh, to the Kingdom of Fife, which is one of the main commuting districts. It crosses the Firth of Forth. The Firth is the Scottish word for estuary, and this is what the Firth of Forth looked like at the beginning of the project in 2008, with two historic bridges already crossing there. There's the 19th century rail bridge, which is a very famous heritage structure, and then the 20th century road bridge opened in 1964. It was Britain's first major suspension bridge, carrying 66,000 vehicles a day, so more than double the traffic volume it was originally designed for. And the story starts back in 2003 when the bridge master for the Forth Road Bridge, hearing about what was going on in the United States when cables were being unwrapped and inspected, took the decision to take a look inside the Forth Bridge cables and found a pretty bad picture. A lot of corrosion, a lot of wire breaks, and a prognosis that the bridge could not go on indefinitely and something needed to be done. And this was combined with other maintenance issues related to the very high volumes of truck traffic on the bridge. So that led to feasibility studies in 2006, 2007, which looked at no-build options, tunnels, bridges on a variety of alignments, and eventually concluded that there should be a replacement bridge on an alignment slightly to the west of the existing bridge. And it's a very special alignment because it crosses right over Beamer Rock, which is a dolerite outcrop in the middle of the Firth of Forth. It's a tiny little outcrop. You can barely see it at high tide. It reveals itself a little bit more at low tide. But that allowed the crossing to be made with a pair of back-to-back cable stay bridges. And this was the proposed design at the start of our studies. And there was triangulated towers to deal with the double main span issue of what happens if you have traffic on the one span and the stability of central tower. And that was really where the crossing cables came into their own, is they allowed a flexible tower on Beamer Rock with a huge reduction in the foundation size, which was good because the underwater blasting needed to create that platform for the central tower was a pretty significant undertaking. It was a design build contract, which was awarded to a consortium, Forth Crossing Bridge Constructors, on April 2011, and you'll recognize a few of the names there, Dragados and American Bridge for sure you'll recognize. A contract duration of 66 months, and it was fixed lump sum payments based on milestone completion. So that's really the background and takes us to the marine risk assessment. So this was something that we did as owner's engineer prior to the award of the design build contracts. And now this is a look down on the Firth of Forth, and you can see there was two navigation channels. The Forth Deepwater channel was the main channel to the container terminals upriver in Grangemouth and Crombie. And there was also container terminals, also transshipment of the North Sea oil. So that was a pretty significant shipping channel. And then there was a secondary channel that went to the port of Rosyth, which was primarily ferries. And one of the things that you see as you look along the channels, and this is the inbound look, so if you're going upstream towards the ports, is that the channels are heading straight towards the South Tower, ST, before they make the bend. And that's pretty significant in terms of the kind of vessel aberrancies and the kind of risks that the bridge might be exposed to because of that bend in the channel right before passing under the bridge. We have developed a vessel frequency distribution. This was surveyed, so this is without growth factors. And you see the two different channels and the number of transits. And this straight away gives a clue as to why a probabilistic study might be beneficial, that some of the largest vessels were over 40,000 deadweight tons. So not the 100,000, 150,000, even 200,000 that we sometimes have to deal with, but still pretty significant vessels with impact forces up to 56,000 kips, but very few number of transits of vessels at that size. And then, the bulk of the transits maybe are more around the 15,000 to 20,000 displacement tons range. And so probably with a risk assessment, we might be able to convince ourselves that we don't need to design for the very largest ships. The risk assessment had a number of different workflows within it, and this shows diagrammatically, and then through this presentation I will go into these different parts in turn. But the engine room at the center of it all is a quantitative risk assessment, similar in some regards to an AASHTO Method 2 risk assessment. But leading into it, it has a few different inputs. Down the center, you have the qualitative risk assessment and review of hazards that the bridge is exposed to. And then you have different acceptance criteria. On the left-hand side, looking at the human consequences of failure. On the right-hand side, looking at the economic consequences of failure. And at the end of this whole study, two different things drop out. One is defining the ship impact forces that will go into the design build contract, and the other is an acceptance by the owner of the residual risk that is implied by those forces. So starting with the qualitative risk assessment, I think this is an important precursor before you get into a quantitative study. And what you can see is it's fairly broad-fronted. It looks at the marine hazard from a big picture perspective. It includes data gathering. It includes stakeholder consultation. It includes establishing the span and the navigational height, and a number of different aspects. And this all creates the picture of what the marine risk is that we're looking at, and helps to make the quantitative risk assessment informed and focused on the right thing. The qualitative risk assessment, it's not just looking at the risk to the bridge. It's not just how likely is the bridge to collapse, but also what does the bridge do for ships. So, we need to take care that the presence of the ships won't, the presence of the bridge won't increase the risk of ship-to-ship collisions, ship groundings, or damage to ships. Even though that the bridge is strong enough, the ship sinks, and so it's still a marine hazard. And then, of course, it looks at the risk to the bridge. And the primary risk that is typically considered by codes is vessel transits under the bridge. But we also were considering maneuvering near the bridge or ships breaking free from adjacent anchorages. And for this study in particular, because a large amount of the shipping was oil tankers, we also looked at the risk of consequential fire and explosion after a collision between a vessel and the bridge. I mentioned earlier the assessment by local pilots. This is always quite an interesting part, I think, of the study. We're all familiar and aware of flight simulators for training aircraft pilots. There are also full bridge mission simulators for training vessel pilots, and that can include putting in changes to the navigation situation, including, for example, the bridge. And we got a very, very favorable outcome from the navigation simulations with the pilots. Now, one thing we did get is we took a bit of a lesson learned from a bridge we worked on in South Korea, where we'd been the independent checker of the marine risk assessment. And that bridge originally had a span of 700 meters, so like 2,200 feet or so. It also had these kind of simulations, but what they did is with the pilots, they put everything on them on day one. So terrible weather conditions, nighttime, things go, a power failure on the ship, everything thrown at them from the very beginning. And the pilots came out sweating. And as a result of that, the span of the bridge was increased from 700 meters to 800 meters. So learn from other people's mistakes. We said, well, for this one, let's work with the pilots to train the pilots in good conditions with the bridge in place. And then when there's a complex scenario that they have to navigate, they're more prepared. And also, I think there's a better understanding that the stress and the workload is related to the situation that they're dealing with and not necessarily the presence of the bridge itself. So moving on to the human consequences of failure and the development of risk acceptance criteria. This isn't codified in the UK, so we had to develop these criteria specific for this project. And we looked at both individual risk and societal risk, with the individual risk being if the bridge was to collapse, what is the likelihood that any given individual might be killed in that accident? And there's two concepts, and one is voluntary risk and one is involuntary risk. If you get in your car and drive to work, you have a reasonable sense that you're taking your life into your own hands, and you know that you can only control some of the hazards that you're exposed to on the highway, and there could be someone could cut you up, or you could be involved in an accident that's not your fault, and worst case, that could be fatal. But I think you have an ability to perceive and understand that risk. But the concept goes that with involuntary risk, people can't be expected to understand that crossing a major bridge could increase their risk because that bridge might be hit by a ship and collapse. And so one of the things to do is to quantify that involuntary risk and make sure that it doesn't significantly change the risk profile of that individual if they're commuting across your bridge every day. And one of the metrics of that can be, well, the bridge road environment tends to be a bit safer. So compared to driving on other road environments, what's the total risk that this person is exposed to driving across the road on the bridge? But a bit of a deeper question is, how acceptable is the accident to society? And I'll go into that a little bit. And this starts to speak to, well, what's the acceptable return period? And one of the things we look at as bridge engineers is quite different return periods for different hazards. So it's important to understand that these are not looking at the same thing. For wind design, it's load and resistance factor design calibrated to a target level of reliability. For earthquake engineering, we're expecting the bridge not to collapse and to meet certain performance criteria in that event. The 10,000-year vessel collision, it's a much higher return period, but that is actually the predicted failure return period. And there's a big difference between predicting the failure return period and designing for a bridge not to collapse under a certain return period and to have certain performance criteria. So AASHTO has pretty set return periods for the failure frequency for vessel collision, and the Eurocode, which was the governing code in the United Kingdom at that time, but relatively recently so. So this was one of the first cable stay, probably the first major cable stay bridge to be designed in the UK to the Eurocode. It wasn't codified. It had some vague guidance on maximum acceptable risk levels, and there's some correlation between AASHTO and Eurocode, although, you know, if you go above medium consequences, you're at a higher return period. But it does explicitly refer to as low as reasonably practical principles for determining whether to provide risk mitigations. And the way that ALARP, as low as reasonably practical, works is that you assess the number of fatalities that could occur in an incident, and you assess the frequency of that incident, and then you look at whether it's acceptable or not. And incidents with a low number of fatalities and a very low probability of occurring are considered negligible. And then incidents which are probable and have a large number of fatalities would be intolerable. But in the middle between those regions is the as low as reasonably practical region, which is a place where you can design within those limits, and you should reduce the risk if it makes sense from a practical perspective. Once you get into the negligible risk zone, you're kind of done. So one of the things was estimating the number of fatalities in the event of a collapse, and the nature of the Queensferry Crossing is that if one of the main substructure units got taken out, a very long length of bridge would collapse. And looking at traffic patterns, we estimated 330 fatalities in the event of a daytime collapse, 20 fatalities on average in the terms of a nighttime collapse. And there was no real correlation between shipping movements and time of day. So we worked with an average of 175 fatalities as, on average, what the scale of the event we might be thinking about. So pretty significant. But one of the challenges we had is, although Eurocode pointed to this concept of ALARP design, we had to develop the boundaries ourselves. And actually, a lot of the original work on this kind of ALARP design took place in the UK in connection with the Canby Island public inquiry in the 1970s. And this was an area in the Thames estuary in southern England where there's a significant concentration of petrochemical plants. And a public inquiry was held to determine if planning permission should be granted to a new refinery. And the investigations in that public inquiry established this kind of concept and the risk levels, and resulted in proposed societal risk curves for an identifiable community in the UK. And those red dotted lines, and they are published, but they were never adopted. And you can see that the red dotted lines don't exactly correlate to what we adopted for Queensferry Crossing. Now, the boundary with the negligible risk level is quite close, and we found a construction industry research report which we could cite, which had a lower level boundary very similar to the Canby Island public inquiry proposal. But for the upper boundary with the intolerable risk, we did not follow Canby Island. And this was in part looking at some of the work that was done on Orison Bridge. And with these kind of curves, they typically have either a slope of -1 or a slope of -2 on a log-log scale. -1 is risk neutral. And if you look at we're looking at the dots there with 10 fatalities and 100 fatalities, and with 10 to the -2 or 10 to the -3, what you see is that a risk neutral curve implies that one accident with 100 fatalities is the same as 10 accidents with 10 fatalities each. A risk averse curve is one accident with 100 fatalities is 10 times worse than 10 accidents with 10 fatalities each. So even though it's the same number of fatalities, it's 10 times worse from a societal perspective. And it was obvious to us and to our client when we were doing these studies that even if Britain had been a risk neutral country in the 1970s, by 2010, it was very much risk averse, and major accidents of the kind of scale that we were talking about have very significant social and political fallout. And so we ended up adopting what we show there as the Queensferry Crossing ALARP region with a slope of -2, intersecting with Canby Island at 10 fatalities, which we felt was the boundary when things started to get of a national scale. And one thing you see of that is a narrowing of the ALARP region. So as the consequences of the accident get more severe, the design boundary that you can move away from negligible risk gets narrower. Just a little comparison of how this might correlate to AASHTO. Now, AASHTO doesn't tell you the number of fatalities associated with the collapse of a typical bridge or an essential critical bridge, but this was the kind of correlation that we made when we were doing these studies. So we felt that AASHTO broadly did fit within the risk neutral approach, but you can see that for some of the larger structures, it potentially doesn't fit within a risk averse approach. So working within this ALAP model, we need to find now a design point within that middle region. And so we did develop an economic model for looking at risk acceptance criteria. And it was based on 3 key relationships. And each one of these relationships makes perfect sense. Looking at risk against capacity, if you increase the capacity of your bridge elements, you will lower the risk of collapse. And the marine collision risk assessment is the tool that you can use to correlate between risk and capacity. Equally, if you increase the capacity of your bridge elements, you're going to increase the capital cost. And you can do schematic design and estimate different scenarios to develop that relationship. And finally, there's this statistical cost against risk, which is quantifying the consequences of failure and carrying out an economic assessment to figure out the expected present value of those consequences. I'll go into that phrase in a minute, but this leads to a statistical cost. And essentially, the more risk that you allow on the project, the higher likelihood that there might be some cost that you have to deal with in the future. And looking at that statistically, there's a correlation. And you can put those 3 relationships together to develop a total economic cost, which is adding the capital cost and the statistical cost, to find an economic optimum where this risk level will in theory be the perfect balance between capital cost and the statistical costs that you're carrying into the future. Looking at that in comparison with the ALAP boundaries, either the economic optimum could be inside of the maximum tolerable red zone towards the top right, in which case your theoretical design point is hard up against that limit, or the theoretical design point could be within the ALAP region, and then that's where you should be in theory designing for. And I've said theoretically a few times, and that's because the actual design point, when you consider public agency decision-making processes and risk tolerance, may not be the theoretical design point. And that is in fact exactly what we found on Queensferry Crossing, was that the actual design point tended to push a little bit to the left. So we did have to evaluate the consequences of collapse. And, as I already mentioned, on average, 175 fatalities. We estimated direct reconstruction costs. Now, obviously, that cost is not what we saw on the capital cost for the whole project, because there were other elements. And also, all of the costs that we see here don't include certain risk factors and additional contingencies. But anyway, direct reconstruction costs of approximately £500 million, and then an economic cost of the bridge not being available for about 5 years. And we actually had the economic studies that that were done to justify the replacement project in the first place. And so we estimated that at approximately £1 billion. Now, there is guidance in the UK about the value of preventing fatalities, and so we were able to put a price on that. And it's sometimes an uncomfortable concept of, what is the price of a human life? But fortunately, there was government guidance here, and it is something, because there are limited public funds available. And so you could either spend your money on making a bridge stronger, or you could spend your money on building or improving hospitals, or perhaps more to the point, a highways agency, a Department of Transport could spend that money, instead of improving the capacity of a big bridge crossing a navigation channel, that money could be spent on dozens of road safety improvements across the state. So you have to decide where best to spend your money. But of course, on these big things, it is very relevant to note that given the severity of failure, we have to expect that the tolerable risk is going to be very small indeed. So I said I'd come back to the expected present value of the future consequences of collision, which is a mouthful, but expected means the statistical average. The present value, I think most of us will be familiar on future discounting of costs, and there was UK Treasury guidance for long-term discount rates on projects, and future consequences of collision is summed up over the entire 120-year design life of the bridge. And we can see how that discounting occurs from, 1.8 billion estimated consequences of collapse, but discounting over time, averaged over the 120-year design life, 825 million pounds. Now, one of the things that certainly the concept of the value of a prevented fatality to me is something that we should be able to wrap our heads around. I must admit, when I was doing these studies, I was the father of a newborn baby, and it was a little bit harder for me to wrap my head around the concept of discounting future prevented fatalities. But fortunately, number one, there was UK government guidance that told you exactly the discount rate to use, and it was a very low discount rate. And number two, it had no influence on the overall decision making. But so one of the things you can see is, supposing we had a 1 in 10,000 year collapse frequency like an AASHTO critical or essential bridge, what does that mean if we take 825 million times 120 years divided by 10,000, just about 10 million pounds. So the statistical cost that you're carrying is not very large compared to potential capital costs of strengthening the bridge. And you can see that as you move to ever increasing ever reducing frequencies of collapse, that cost diminishes each time. And we could put this data together, and we did, exactly to develop those relationships that I showed earlier on. Before they were shown theoretically, here we developed them for the project. And for the most exposed elements, we did tend to find that an economic analysis was pushing us towards the right-hand boundary of being close to the maximum tolerable risk. And for some of the less exposed elements, we were more inside the ALARP region. Another consideration which influenced decision making was the environmental impacts associated with higher capacity. So, you won't see vessel collision dolphins on this bridge, but we did think about it, and the costs and environmental impacts weren't justified. The bridge is significantly strengthened in some key areas so that the foundation units themselves are strong enough to resist vessel collision up to a point. Which takes us to the engine room, the numerical calculation, and this is the thing that is closest to an AASHTO calculation, but some differences within the UK and Eurocode system. We did use a GIS analysis based on data that we got from automatic identification systems trackers on ships to develop vessel transit paths, to develop speeds. And we can see the probability of collision with different elements. And just like we saw from that helicopter view earlier on, the South Tower is very exposed to collision in particular. And of the piers, the pier S1 is the most exposed of all the piers. Although it's a lot less exposed than towers, of course, the towers in a cable stayed bridge will naturally have a lot of strength just to resist the vertical loads, whereas the piers, maybe less so. AASHTO is a holistic model of vessel collision. So it calculates the aberrancy per vessel transit, and it basically says 1 in every 17,000 transits, there's going to be a ship that's gone wrong crossing the center line of the bridge. And let's use a standard deviation bell curve as like where that ship might be. Eurocode, on the other hand, is scenario based. And rather than it saying there's certain aberrancies, like 1 in 17,000 times a ship passes the bridge, there'll be an aberrancy. It does a per unit distance aberrancy. And so then the geometric probability has to track the behavior between the point of aberrancy and the point of collision. So Eurocode is clear that it's different to AASHTO, but what it doesn't do is give you any of the parameters needed to actually do the analysis. And it doesn't provide references either. So you have to go and figure all that out for yourself. Not ideal. Now, AASHTO is completely on the other end of the spectrum where every parameter is given. And so you can do a full probabilistic risk assessment really just straight out of the code. And that's very convenient sometimes, but also potentially it can lead to certain things being missed. So I think neither extreme is necessarily ideal, but Eurocode certainly makes for hard work to carry out that study, but it's very clear it should be scenario based. So we developed a model that was, looks quite similar to the AASHTO model in terms of its number of different conditional probabilities based on the Eurocode, and developed a model of post-aberrancy behavior that basically said at the time of aberrancy, the vessel will be on its transit path with some deviation of position, and then afterwards it will on average head in the same direction, and the further it gets away from the point of aberrancy, the more broadly it may have spread, the more uncertainty in the position. We looked at various research documents and studies to develop base rates of aberrancy, and you can see there are frequencies per ship hour of propulsion failure, steering failure, human error, and there is data out there that says these kind of failures on a ship do happen, with a degree of regularity that is predictable on a statistical basis. And another important part of the Eurocode approach, if you look at the aberrancy at a point, then what about the probability of avoiding collision? So based on discussions with local pilots and mariners, we developed models of the ability of a vessel to recover. And what you find with this kind of scenario-based approach is if you have a square transit, like on the left, which is like the outbound fourth deepwater channel, it matches very closely to AASHTO. And in fact, you can see, where the piers are, it matches very, very closely. In the middle of the channel, the Eurocode Queensferry Crossing model shows a higher probability of an aberrant vessel being there. But these vessels are basically, they're becoming aberrant as they pass under the bridge center line, and anyway are staying within the channel. So they're not truly an aberrancy in terms of they're not exiting the channel. But it's a completely different picture when you compare the inbound, and you can see that double lobe, which is representative of the vessels are heading straight towards the South Tower before they make that bend. So any aberrancies on the inbound vessels before the bend will lead to ships being in the vicinity of the South Tower and Pier S1. And then the red dotted line, the modified collision probability, that was filtering out vessels that hit other objects before they get to the bridge, including, for example, the existing rail bridge. We also had to develop a probability of collapse function, and in AASHTO there's a Heinrich ratio, which is basically if the impact force is 10 times higher than the resistance, then the probability of collapse is 10%, which you have to read that a few times to wrap your head around it. But it's basically based on the premise that not all accidents are as bad as they might have been, and it's based on research on ship-to-ship collisions that was carried out in Japan in I think the 70s. And there are a lot of reasons why accidents might not be as bad as you thought it was going to be. A chance to slow down, maybe a glancing blow, a drifting ship, and partial safety factors, lots and lots of reasons. And we developed a project-specific collapse function looking at the resistance of the elements and thinking about their variability, and then with two different impact forces, one for the frontal and one for the hull, and saying, well, 80% of collisions are probably not going to be a frontal impact. And putting those two curves together, we could develop a probability of collapse. But it's hard to find the AASHTO probability of collapse function if you take an approach of developing, developing your own. But anyway, so we used that more conservative approach. We used the blue curve, which still has probability of collapse in that if the impact force is significantly higher than the resistance, that's the nominal impact force and the nominal resistance, there's still only a probability of collapse. But by the time you get to the impact force being 10 times the element strength on the Queensferry Crossing curve, you are getting close to 95% chance of collapse. So all of that modeling allowed us to get to different probabilities of failure for different elements, and the towers broadly grouped around the same kind of spot, although the south tower was more exposed to inbound transits, it was less exposed to Rosyth. But Pier S1, the triangles, did really stick out compared to all of the piers, that it was much more exposed than other piers. So then this essentially was the result of the engine room was developing these exposures, and it takes us back to the decision making that the client has to make. The two things that drop out of the bottom, the definition of the ship impact forces and the acceptance of the residual risk. And these were decisions that were made by a financial advisory group for the project. And they were quite comfortable with making these kind of decisions for acceptance of risk at a more regular scale, where you say, like, should we invest this much money in an intersection improvement scheme? Slightly more challenging to ask them to make decisions on very, very, very small probabilities of very high consequence events. But anyway, this was information that we took to them, and we were able to compare the design that we had at that time, the so-called specimen design, with strengthening the bridge to get to a negligible risk level. And it would have cost another 120 million pounds or so to get to a negligible risk level, but with the benefit only being like 0.3% of the cost. So really not worth getting to that level, and better to take that acceptance of residual risk. But what we did find is S1 really became quite an interesting case. To resist the service loads, it needed a capacity of 6,700 kips. Eventually, in the design build contract, we required a capacity that was 2.5 times that, which had an estimated cost of about 15 million pounds in different additional capital costs. But the benefit was only about 1.4 million pounds. So it really, on a straight cost benefit analysis, it did not stack up. But the decision by the financial advisory group was really motivated by trying to avoid that Pier S1 was an outlier. So when they see the top chart there, and then they see that pier having so much more risk than all of the others, they actually asked us to develop what they called an equivalent risk design as well, do enough strengthening so that pier is in line with the other substructure elements. And so I think that really comes back to as low as reasonably practical. The word practical is important. It doesn't mean designing to that theoretical bottom point of a benefit to cost ratio of 1. It means designing in a way that makes sense based on having the information about the costs and benefits of different scenarios. And this was what went into the contract. We had the resistances for the different substructure units. we had a 2-level design where there was a repairable damage level with some lower level impact forces, and that was what the design builder then designed the bridge for. So conclusions on this are, there's a lot of engineering judgment goes into these kind of studies. Even if you're working with AASHTO, where a lot more of the parameters are codified, there's still a lot of engineering judgment, because for a bridge of this complexity, if it was designed in the United States, you wouldn't want to pick up AASHTO and just use it without going through that qualitative risk assessment first to make sure that you'd identified all of the hazards. Some of the risk acceptance side might be a little bit more dealt with already, but there would still be a lot of judgment. And some of this is in a gray area. You can tell when things are okay, you can tell when things are not okay, but within that gray area of judgment, you really want that to be a discussion with the owner. And so that brings itself to, what does this mean in design build? So this risk assessment, it took 18 months because it was done over multiple phases. And with that engineering judgment for these non-codified aspects and the need for approval from Project Financial Advisory Group, it didn't make sense to ask the design builder to repeat the risk assessment. To some extent, it creates a conflict of interest unless all of the parameters are tightly specified, because on a fixed price design build contract, there's always the motivation to take those parameters in the middle and dial them towards the end of reduced cost. And it's also extra design effort. Why ask the design builders to repeat such a comprehensive study? So in this case, the owner retained liability for the risk assessment and specified the forces. And because of that, we carried out an independent check so that that aspect of the design, which the owner retained liability for, was checked. Now, progressive design build somewhat changes this paradigm because you can work collaboratively with the owner. And so that removes that conflict of interest as you work collaboratively together to develop a GMP, and the decision making can be made jointly. And some of what we've maybe taken away thinking about AASHTO-based analyses, and these are just observations, they're not recommendations, but the first principles approach is more time-consuming, but it does mean that you end up being more tailored perhaps to the specifics of the project. And so for some bridges, this scenario-based approach will be more important, will be more appropriate. And particularly if you're analyzing complex waterways. And the 1 in 10,000 year collapse frequency, does that cover all of the bridges? If is the United States a risk neutral or a risk averse country? And an observation is we've developed project specific fragility curves a couple of times now, these collapse functions, and we always get a more conservative result than the codified Heinrich ratio of 10 times a force that's 10 times the resistance leads to a probability of collapse of 10%. We can't reproduce that when we develop a project-specific fragility curve. All right, well, thank you. That was a rattle through of a lot of work in a brief period of time, and yeah, very happy to take questions. Wade, did you want me to stop sharing or?
Nope. You can, you can just share that screen. That'll be a nice placeholder. And if any of the questions that come in require you to move back and forth through your presentation, then it'll be easier that way.
Okay, great.
All right, so we've got a few questions rolling in here. First of all, if you could, Matt, I think you probably explained it towards the beginning, but if you could just one more time review for the audience, what was Arup's role on the project? Were you representing the owner or the design build team?
Sure, yeah. So Jacobs Arup joint venture was owner's engineer, and so we were in an integrated team with the owner.
Okay, so the vessel collision study that you all performed was prior to the procurement process for the design build teams.
Correct, yeah. It was in the development of the preliminary engineering and technical requirements.
Okay, great. So the design, the span layouts and everything that were set up, we would call that maybe like the base design or something like that in the US, ahead of the design build procurement. How much freedom did the design build team have to, say, adjust tower or pier locations, and what was the process for doing that?
Yeah, that is actually a great question. Yeah, so for this particular project, we used a definition design, which was also adopted on Orison Crossing and on, within North America, Samuel de Champlain Bridge. People may be familiar with it, which meant that the owner wanted to control the architectural design through objective requirements, which meant that limited freedom for moving substructure unit positions. So the span length was essentially already determined, and there was a little bit of flexibility in the position of pier S1, but not a lot. And that obviously is consistent with the owner providing ship impact forces to the design builder. So because if the pier locations were unknown, you wouldn't really be able to do that. So one of the benefits of the definition design, it was originally for architectural requirements, but one of the benefits was that the owner could also therefore own the risk assessment, which frankly they wanted to do. They wanted to make these difficult decisions together with an owner's engineer, and then ask the design builder to build a project with the vessel collision capacity that they had decided to take.
Okay, great. And that kind of leads to the next question. What are your thoughts on a similar sort of design build procurement where the vessel collision studies or the vessel collision risk determination is left up to the design build proposers?
I think, and if it's progressive, then that's different. But if, let's say, if it's a traditional design build procurement, I think that the owner should have a pretty good understanding of vessel collision risk. And let's say if you take Tappan Zee Bridge replacement, Governor Mario M. Cuomo Bridge, I mean, on that one, it makes a lot of sense to transfer the design to the design builder, because the navigation channel is in a clearly understood position. The approaches from both directions are square and orthogonal, so there's no real complexities, there's no adjacent mooring, and anyway, like the level of vessel collision risk is relatively small, because it's there's not major shipping transiting that location. So that's a perfect case where there's no need to do anything other than follow AASHTO and just let the design builder do an AASHTO straightforward design. If there's a more complex waterway, adjacent ports, or other project specific factors, I think the owner would want to make very clear how AASHTO should be applied, to give very, very clear guidance to the design builder, so that the design is it doesn't leave like that kind of risk judgment call being transferred to the design builder. I think the owner should decide on the balance of upfront investment versus residual risk. The design builder should have very, very clear guidance on how much residual risk the owner wants to take.
Right. Yeah, because those kinds of decisions could influence the bid price, but the flip side is it also influences the risk. So you may have an uneven playing field between different design build proposers.
Right, you don't want to be having a lower price because you're taking on extra risk. You want to be having a lower price because the design builder has come up with, great innovations to design and build this bridge in a cost-effective way.
Yep. Okay, good. That's fascinating, and it's interesting that the owner, I'm assuming the owner's engineer team, identified some of the complexities for this particular site and this particular situation where, perhaps some more guidance from the owner was necessary. So that's great. Got another question. Have there been attempts to verify some of the assumptions that were done or taken during this vessel collision study over the service life of the bridge to date?
There is some work going on to review the marine traffic forecasts. So yes, there's ongoing work to make sure that the changes in shipping within the channel are in line with projections that were made at the time of design.
Great. Okay. Maybe that can be a presentation about the comparison long term between assumed and actual. The independent peer protection systems that were rejected partly during the environmental review process. Did the environmental impact dominate that decision at the in terms of how it changes the risk assessment? How did the decision-making process go there in terms of balancing environmental impact versus risk assessment?
Yeah, in this case, the environmental impacts did not dominate the decision making. The decisions were made by the financial advisory group, and it was a two-step process of a check-in and presentation of where we were, and then some comments and feedback from the advisory group. And the financial advisory group was basically a government committee that was set up to oversee and audit the project to make sure that big picture decisions were an appropriate investment of public money. And then we went back to that same group with updated data and information based on their comments from the first time around, and eventually they elected to go, as I said, with that equivalent risk design. And so really the cost and cost benefit and risk factors were primary, and the environmental impact was noted as, if we provide these additional structures, not only will it have an increased cost, but also it will have an increased environmental impact. But we didn't need to go to that next step of a detailed impact assessment of those structures, because a decision was made prior to that.
Okay, great. Kind of a big picture question, and I don't want to put you on the spot, but are there any requirements or steps that are in the Eurocode that you would recommend that AASHTO consider adopting or changing their methodology?
Yeah,
I know
that's
it's a big picture question.
Look, I've been thinking about that a lot over the last few months, and at the highest level, I think that AASHTO should consider separating out critical from essential bridges, and that critical bridges, there should be some consideration of what are the parameters under which an AASHTO method 2 analysis would not be appropriate. I think that if we're going to reflect on what happened and make changes to the code, we should focus on that subset of bridges, the bridges which cross the busiest channels with the highest consequences of collapse. And I think, you know, maybe I should go all the way back. You said I could refer back. Yeah. This slot out here.
Mm.
And I'm not necessarily saying that it should just be a 3-step process and that this yellow line should be down here. I think it should be more, you know, if we're out here, how are we analyzing?
Interesting. Yeah, it is interesting. There was that level of disparity between, you know, the results that you guys had with the Eurocode and what AASHTO would have given you. Definitely food for thought.
Hmm.
One more question. We didn't really talk much about vertical clearance, but was the vertical profile of the bridge and the vertical clearance determining that part of this vessel collision study?
It was. We did have to do a span and air draft assessment. The vertical clearance was relatively straightforward because the 2 adjacent bridges, and there was consideration of, you know, should the bridge be raised in order to provide for potential future expansion if the other 2 bridges are replaced. But the other 2 bridges are grade 1 listed structures. It's kind of like planning for the replacement of Brooklyn Bridge. You don't get very far because people are like, well, that's never going to be replaced. So
yeah, the
you know,
Firth
by and large,
Bridge
it was
isn't going
making
anywhere.
Yeah, exactly.
Yeah.
But the
Understandable.
span was very much set by those navigation simulations that I spoke about earlier on to make sure that the piers were, you know, the towers were set back far enough.
Yeah. Okay, great. There's a question here about providing references from the study that you showed. Perhaps when we send out a link to the slides, that can help out a little bit. But I think, did you cite some of your references in the slides here?
I don't think I did, but I can provide some references. I can provide as a first instance a peer-reviewed and published paper. So why don't I send that to you right after this, and I'd be, you know, it's fine for that to be distributed to attendees, and that has some of the references, and then if there are specific references to particular technical aspects of, like, how did we develop the you know, aberrancy rates per ship hour or whatever, I'd be happy if people reached out, happy to share.
Great. Oh yeah, that'd be great to get access to that paper. That sounds really interesting. All right, very good. Well, we're about 10 past the hour now, so I think we'll call it good for today as far as Q&A goes. And Greg, we'll turn it back to you to finish this out. I might have caught Greg off guard there.
Yeah, seems like it.
Yeah, all right. Well, maybe Greg's microphone isn't working. Nope, we can't hear you, Greg. All right, that's fine. We'll I'll conclude today's festivities. Appreciate everybody attending, and look forward to a link to the presentation and the slides being posted on the ASBI website in about a week or so. and also the PDH certificates will be sent out in approximately a week. So thank you everyone for your time today. And Matt,
Yep,
thank you
thank you,
very much
everybody.
for your presentation. Very, very interesting.
Thanks, Wade.
Thank you, everybody.
Great questions. Thank you, everybody, for your time today. Appreciate it.
All right.
Yep.
Bye.
All right. Bye-bye, everybody.